result that we can derive using Reynolds transport theorem. So using Reynolds transport theorem and conservation of mass, is the following. Okay, so let's say n of system is, so the property now that I am interested in is mass. Okay, so then n of system is the mass of the system. Then if this is the case, what would be eta? Eta was nothing but n system by mass of the system. So this is mass by mass, which would become 1. So eta is 1 for this case when your n system is 1, right? So now we'll use Reynolds transport theorem. So this would become dm by dt for a system. This would become equal to d by dt integral eta rho dv over control volume cv plus control surface eta rho vxyz dA, eta rho vxyz dot dA. Okay, now we know that if mass is conserved for the system, this quantity dm by dt for the system would be 0. Okay, so what would this become? So this gives us d by dt integral over control volume eta rho dv plus integration over control surface is equal to 0. So this is the first relation that we derive. Now in most of the problems you will be given that the fluid that you are dealing with is incompressible. Let's just write it over here. So you will be given that the fluid that you are dealing with is incompressible. So if the fluid is incompressible, what does it tell me? It tells me that rho is a constant quantity. Okay, so if rho is a constant quantity, what I can do then is I can take it outside of the integral, right? Oh, and since eta is equal to 1 in this case, we should write instead of eta 1, and 1 into rho would be rho, so it would look like this. Okay, so now if rho is constant, I can take this rho outside of this integral. Okay, so then what would this equation would become? So this would become d by dt, and this would be independent of time as well, so I can take it outside of this derivative also, and this will become d by dt of integral cv dv plus cs, rho is taken outside, vxyz for dA equal to 0. Okay, now if I ask you what is this term, okay, think about it. So this term is nothing but the rate of change of volume of control volume, right? And since we are defining control volume in such a way that its volume remains constant, right? So this term is telling me that this is the rate of change of your volume of CV, control volume. But d by dt of volume of control volume is 0 because volume of CV is constant. Thus this term would become 0 and we'll be left with rho integral over rho, and since this, okay, let's just write it first, xyz dot dA is equal to 0. This would mean, since density is not 0, this would mean that I can just write integral over cs vxyz dot dA vector equal to 0. Okay, so we arrive at this equation using Reynolds transport theorem. Next, and this is only for incompressible fluid, okay, where rho is a constant, so constant in space and constant in time. Okay, to understand the applicability of this equation, let's do a quick problem. So let's consider a pipe. Okay, in which we have a fluid flow like this. Okay, and now let's say you are given a question that velocity at this point is given to be velocity at this point is given to be, let's say, some v vector. Okay, let's say just v1 vector. Velocity at this point is given to be v2 vector. Now you are asked a question that what is v3 vector, and also these areas are also given to you in the question. Okay, this areas of cross section are given to you in the question. So this is given, and you are asked what is v3. Okay, so let's say this area is a1, let's say this area is a2, let's say this area is a3. Okay, now how we'll use the Reynolds transport theorem, or particularly this expression, this equation, to find v3. Let's understand that. So first let's draw a control volume. So how the control volume would look like? So for our convenience, we would draw a control volume like this. Now why I am drawing control volume like this, it will be clear. It will be clear to you in a couple of minutes. Okay, so this is my control volume. Okay, all right. So what are the different surfaces in this control volume? So one surface is this one, let's call it surface 1. One surface is this one, let's call it CS2. One surface is this one, let's call it CS3. One surface this one, let's call it CS4. One surface this one, let's call it CS5. One surface this one, let's call it CS6. Okay, and also let's say in the question it is given to you that assume fluid to be incompressible. And find v3 with given v1, v2, a1, a2 and a3. Okay, so now since it is given that the fluid is incompressible, I can use this equation. Okay, so let's just use this equation. This equation tells me integral over the control surface with integrand vxyz vector dot dA vector should be 0 for my control volume. Now since this control surface is made up of different surfaces, I can write it like CS1 plus CS2 plus so on. Okay, so let's just write it CS2 plus CS3 plus CS4 plus CS5 plus CS6. Okay, so I can write this term, I can write this equation now as integral over CS1 vxyz dot dA vector. Now what is this dA vector? So if this is my CS1, dA vector on this is some elemental area. Okay, and this, by convention, we use dA vector, we define dA vector pointing outside of the surface, so this would be my dA vector for this. Okay, alright, so now we can write this as plus CS2 vxyz dot dA vector. Now what is this dA vector? This dA vector is somewhere over here. Okay, with dA vector like this. Alright, similarly this would become CS3 vxyz dot dA vector plus CS4 vxyz dot dA vector plus CS6 plus integral CS6 vxyz dot dA vector equal to 0. Okay, now what is vxyz? It is the velocity of the fluid on the control surface or across the control surface with respect to the control volume. Now since this control volume is stationary, so this velocity v1 will be with respect to CV also, this would be v1, because vxyz, which was equal to the velocity of the fluid minus the velocity of the control volume, would become v fluid, since vCV is 0 currently. Okay, and v fluid given is v1, v2 and v3. So we can directly use v1, v2, v3 in some of these surfaces to replace vxyz vector. Okay, now just see this control surface. Let me just use some other color. See this control surface. What can you say about vxyz dot dA vector on CS2? What can you say on this surface? So let's just again draw CS2. Let's just take only CS2. So this is your CS2. The fluid is flowing like this. Okay, and the dA vector on the CS2 is pointing like this. Okay, so this is your v vector. V vector dot dA vector is 0, right? Because v vector and d vector, the angle between them is 90 degrees, so that's why V dA cos 90 becomes 0. Now the similar argument I can give for CS4 as well. Okay, so CS2, this term, so CS2, this would become 0. Similarly, this is my CS4, and again V dot dA is 0 for this. So again, so similarly CS, not CS3 but CS4, integral over CS4 is 0. I forgot to write CS5. So integral over CS5 Vxyz dot dA vector. Now similarly CS6, for CS6 also this would be 0. So now we are left with this term, and this term. Okay, we are now left with 3 terms. Alright, so let's just write them. So this is integral CS1 Vxyz dot dA plus integral over CS3 Vxyz dot dA plus integral over CS5 Vxyz dot dA. This should be 0. Okay, now we are given that the velocity across, so let me just again draw CS1. So this is my CS1. Okay, since this is some hypothetical surface, I should draw it with the dashed curves. Okay, so this is CS1. Velocity, it is given that the velocity of the fluid on this surface is v vector. So it is given that the velocity is v vector, and what would be dA? So dA vector would look something like this. So what can I say about v dot dA? V dot dA is minus v dA, right? So let's just write it. For CS1, angle between v vector and dA vector is 180 degrees. Okay, this thing implies Vxyz, this V is nothing but Vxyz, so Vxyz dot dA will be Vxyz and dA cos 180. What is cos 180? Cos 180 is minus 1, so we can write this as like this. And given in the problem that this Vxyz is V, so this will become like this. And since this is, so just okay, let's do similar analysis for CS3 also. So this is for CS1. Now similarly for CS3, what would happen? Now on CS3, so let's just draw CS3. CS3 looks something like this. So this is my CS3. Again, let's draw it like this. So this is CS3. The velocity vector is v3 on this, and if I make a dA vector would point something like this. So what is the angle between v3 and dA? It is 0 degrees. The same implies Vxyz dot dA vector on CS3 will be equal to Vxyz dA cos 0. Cos 0 is nothing but plus 1, so it would look like this. Okay, and Vxyz is v3 here, so this will become v3 dA. And for CS5, how CS5 is looking like? It's looking like this. Again, I'm making the same mistake. Okay, so it looks like this. This is your v5, and if this is your dA vector would look like this, and Vxyz dot dA, since again this is, the angle is 0 degrees, I can write Vxyz dA, and Vxyz is V3 here, so V3 dA. So let's use Vxyz vector dot dA vector for CS1, CS2, CS3 and CS5 in this equation. So let's do it quickly. So now it is CS1 so it is CS1 minus V dA plus CS3 VDA plus CS5 VDA equal to 0. Oh sorry, so this is V1, this is V3 and this is V5. Okay, and what we wanted to find was, okay, so the velocity vectors are V2 and V3. Okay, so this was V2 and this was V3. So this is V2 and this is V3. Okay, V2 V3. So V3 is unknown, and since so we need to find V3 from this equation. And now given that V1, V2 and V3 are some constants independent of position of dA. Okay, so let's say your control surface is like this, and you have drawn dA here, or you have drawn dA here, or you have drawn dA here. Then this V is a constant value, either it is V1 or V2 or V3 on CS1, CS3 or CS5. Okay, so this means that I can take V1 outside of this integral, V2 outside of this integral, and V3 outside of this integral, right? Okay, so this would become minus V1 integral dA CS1 plus V2 integral dA CS3 plus V3 integral dA over CS5 equal to 0. Now what is dA integrated over CS1? So that would be nothing but area of CS1, and this would become area of CS3, this would become V3A of CS5 equal to 0. Now A CS1 is actually equal to the area of this cross section, right, which is A1, and area of CS3 would become is nothing but area, given area A2, and area CS5 is nothing but area A3. So we can write it here. So this is A1, A CS3 is A2, and A CS5 is A3, and these are known to us. So let's just write it over here. So this would become minus V1 A1 plus V2 A2 plus V3 A3 equal to 0. Okay, so we'll get unknown quantity V3 equal to V1 A1 minus V2 A2 divided by A3. So this is your answer. So I hope now you understand how we can apply Reynolds transport theorem and the further equations that we derived using Reynolds transport theorem. For example, we just derived by taking n system equal to mass, we arrived at this expression. Okay, so we arrived at this expression. and we used this expression, which was for incompressible fluid, to solve our given problem. Okay, so this was using RTD and also for given incompressible fluid. Okay, so similarly, let's say if I am given n1 number of inlets and n2 number of outlets, and given the fluid is incompressible, then I can write summation I equal to 1 to n1 ai vi with a negative sign, because for inlets, if this is your inlet, so let's say this is your inlet, then velocity vector would look like this and area vector would look like that. So v dot dA will always be negative, so that's why negative sign is there, and I have removed the dot product. Okay, plus summation over j is equal to 1 to n2 ai vi equal to 0. Okay, so this is a general expression when a fluid is flowing and you are given that n1 is the number of inlets, n2 is the number of outlets, the fluid is incompressible, and vi ai are the fluid velocities and area of cross section I. For ith cross section. Okay, now let's use this general formula for the case which we already solved for. So we were given this problem like this was our pipe. Okay, this was given v1, this was given v2, this was given v3, the area was a1, the area was a2, the cross section area here was a3. Okay, now if I just see this equation, what are the number of inlets? n1 equal to 1. What are the number of outlets? Number of outlets are 2. So how would this equation be written like? So I will write minus summation I equal to 1, and since n1 is still 1, so this will become summation I equal to 1 a I v I, where I is the number of where I is the ith inlet. So here ith inlet is this inlet. Okay, what is the area? Area was a1. Area here is a1. What is the velocity? Velocity of fluid is v1 plus summation j is equal to 1 to 2, since there are two outlets aj. Okay, so I should, this is aj vj equal to 0. So this would give me two terms. One is a2 v2 plus a3 v3. So this would become a1 v1 plus a2 v2 plus a3 v3 equal to 0, and this matches with this equation. Okay, alright, so this is minus a1 v1 plus a2 v2 plus a3 v3 equal to 0, and this also gives me minus a1 v1 plus a2 v2 plus a3 v3 equal to 0. Okay, let's say we have another problem. So let's say we have n1 number of inlets with density. So let's say we are given different fluids with fluid density rho I at ith inlet, and N2 is the number of outlets with fluid density rho j at jth outlet. Okay, so then how would the equation look like? So in that case, the equation would become minus over summation I is equal to 1 to n1 rho I ai bi plus summation j is equal to 1 to n2 rho j aj vj, okay, equal to 0. Okay, so you can remember this equation like this, or you can also remember this like this. So summation over all the control surfaces rho a vxyz and this is for a particular control surface I. Okay, summation over CSI, where CSI is from 1 to total number of control surfaces, summation over that, and the term here is rho a vxyz, where all these three things rho a and v are for that control surface CSI. Okay, so let's remember the equation like this. Okay, and this is the case for when all the fluids are incompressible and the given flow is uniform. Okay, and please note that since we have not made any assumption on whether the fluid is whether the flow is steady or not, so that's why this equation is for steady and unsteady flows. Okay, and if we consider that there is only one fluid in all the cross sections, then we can take this rho outside, and since rho times something is equal to 0, that something has to be equal to 0. So in that case, this equation would look like this, equal to 0. Okay, so this is when one fluid is there. Okay, so let me just repeat how we reached to this equation. So we used Reynolds transport theorem and using mass as the extensive property plus the conservation of mass, which is nothing but dm by dt equal to 0, we arrived at this equation. Okay, all right.